We continue towards the fundamental theorem of arithmetics, and the first step of our journey is Euclid's lemma. This is theorem 1.1 in the book, and the theorem says that let a and b the integers and b a positive integer. Then there exist two integers which are unique and which we call Q and R, such that A equals BQ plus R, and the integer R is bigger or equal than 0 and strictly smaller than B. As the name suggests, Euclid's lemma was found by Euclid some 2,500 years ago. The book calls it division algorithm. And that is because the lemma claims nothing but our ability to divide one integer a by another non-zero integer b with a remainder r. R is nothing but remainder from division. Euclid was probably the first who realized that this is not an experimental fact and may be proved starting from more obvious properties of integers. The idea, which is reflected in the name division algorithm, is very simple. Assume Ra is positive. Then how do we divide it by b? We repeatedly subtract b from a several times, q times, until the remainder r becomes smaller than b, and stop at this moment. The proof is nothing but a formalization of this very transparent idea. The proof consists of two facts, two steps, because the lemma, the theorem, if you want, has two clauses. These are existence of Q and R, they exist, and they are unique. We start our argument with the second clause, with uniqueness. assume, for the sake of contradiction, that there are two pairs of numbers. Q1 R1 and Q2 R2, meaning we can write A as B Q1 plus R1, and we can write A as B Q2 plus R2. And we've got to assume that they are different. Q1 is different from Q2. Because if Q1 is equal to Q2, then automatically R1 is equal to R2, because R is nothing but A minus BQ. If you take Q1 same as Q2, you get same R1 and R2. Otherwise, R1 is equal to R2, and we are done. So we have to assume, for the sake of contradiction, that the two pairs Q1 R1, Q2 R2 are different, and that boils down to Q1 is different from Q2. Then we subtract the two equalities. A cancels out, and what we produce is B times Q1 minus Q2 equals R2 minus R1. We subtract the bottom one from the top one and rearrange the terms. Take the absolute value of both parts to get absolute value of B times, which is actually the same as B itself, B was assumed to be positive, times absolute value of Q1 minus Q2 equals absolute value of R1 minus R2. Oh, let me write, because it doesn't matter, R2 minus R1. This is the same thing, because we took absolute value. Doesn't matter whether it is R1 minus R2 or R2 minus R1. Now let us look at this equality. The left-hand side is B, or absolute value of B, if you want, is the same thing, times a non-negative integer, actually strictly positive integer, because we assume that Q1 is not equal to Q2. So this difference Q1 minus Q2 is not 0. Its absolute value is at least 1. Thus, we have the product B times absolute value Q1 minus Q2. Same thing as B times absolute value Q1 minus Q2 is bigger or equal than B, because this is a positive integer, at least 1. At the same time, the right-hand side is smaller than B. Simply because both of them are in between B minus 1 and 0. This whole distance is B minus 1, and somewhere here are R1 minus R2. R1 and R2. So the distance between them cannot be bigger than the whole length of this interval, which is B minus 1. So this difference is simply the length of this interval. The maximum length will be B minus 1. So it is at most B minus 1, so it is smaller than B. So we found that the left-hand side is bigger or equal than B, while the right-hand side is smaller than b. This equality cannot hold. So this equality cannot hold. That is a contradiction. We derived an equality which cannot hold, which is that our assumption was wrong. We assumed, for the sake of contradiction, that Q1 is different from Q2 and found an impossible inequality. Thus, Q1 must be equal to Q2, therefore R1 must be equal to R2. The second part of our proof is existence. For existence, we consider a set S, which consists of all integers of the form a minus bx, where x is also an integer and a minus bx is non-negative. This is a set of course, a is integer, b is integer, x is taken to be always an integer, so this is a set of integers. Again, we took all integers x such that a minus bx happens to be non-negative, and took the set of all this a minus bx. This S is a set of non-negative integers by its very definition. We took only non-negative integers as members, elements of the set. We want to convince ourselves that S is not empty. Because we can always take x, because put it so, for x equals negative absolute value of a minus bx is non-negative, therefore a minus bx is an element of S. Why, when x is negative absolute value of a, the integer is non-negative? We've got to write some inequality. So this inequality means that we want to check a minus minus, and this minus give us a plus, a plus b times absolute value of a. We want to prove this is non-negative. So we want to support this claim. All right. What is absolutely clear? B is a positive integer. So anyway, so we want to support this claim. Anyway, what we know is that b times absolute value of a is bigger or equal than absolute value of a. Because b is a positive integer. Positive integer times some not a positive integer is bigger. B is being a positive integer. B is at least 1. So we have this inequality. And this inequality gives us that our a plus b absolute value of a is bigger or equal than a plus absolute value of a. A plus absolute value of a is, if a was positive, this is 2a bigger or equal to 0 if a is bigger or equal than 0. So if a is non-negative, then absolute value of a is equal to a, so it's twice non-negative integer, bigger or equal than 0. If a was negative, then absolute value of a is negative. A and they cancel, we get a 0. Zero if a was negative. In either case, our quantity of interest is bigger or equal than 0. This claim is supported, justified, if you want. Thus, what we found that this set S is not empty. This is a set of non-negative integers. We took only non-negative integers as elements of S, and we found that this non-empty, it contains at least one element. Thus, we can conclude it has a minimum element. That is where well-ordering axiom is used. So, well-ordering axiom allows us to conclude that S has a minimum element, has the smallest element, call this element R. That is, for some x, a minus bx is equal to R. Call x integer such that a minus bx equals r. Such integer exists. This is an element, r is an element of S. Call this x q. This is x such that a minus bx is r. Thus, a minus bq is r. The only thing we have to check in order to convince ourselves that these are r and q, which Euclid's lemma claims the existence as these inequalities. Let us check them. So we got to check that R, the smallest element in the set S, satisfies these two inequalities. Here is the definition of S. All elements in S are non-negative. So we can immediately say that one inequality is obviously true. R is at least 0 because R is an element of S. Minimum or not. It is the smallest element, but still an element of the set. For every element of the set, this element is non-negative. The set was assembled from only non-negative integers. Another inequality to check, R is smaller than B. Well, clearly, we have to use the fact that R is not merely an element of S, but this is the smallest element of S. R is smaller than B because R bigger or equal than B would not be the smallest in S. Indeed, take for R bigger than B, so if R bigger or equal than B, and R is an element of S, then R, as any element in S, is a minus bx for some integer x, and we can take not integer x, but integer x plus 1. A minus b times x plus 1 is equal to a minus bx minus b, which is r minus b a minus b times an integer is anyway an element of S as soon as a minus b times integer, if it is non-negative, it is an element of S. So a minus b times integer is an element of S. So if r bigger than b, bigger or equal than b, is an element of S, then r minus b is again of the same shape a minus b times integer, and positive because r is big, non-negative because r is bigger or equal than b, so it is again an element of S. So if r is bigger than or equal than b, then it may be an element of S, but cannot be the smallest among them. That's it. We proved two inequalities. Thus, we proved this double inequality. And that finishes the proof of Euclid's lemma. Again, what we did is nothing but a formalization and some enhancement of the idea that we can subtract repeatedly b from a. So that justifies our ability to divide integers with the remainder. This argument, possibly not in exactly this form, but in an equivalent form, was found by Euclid long ago. And in fact, this lemma is absolutely instrumental in our approach to the fundamental theorem of arithmetic. That was exactly the approach Euclid took to prove the theorem, and later on we will follow this approach. Thank you for listening.